The first topic of this chapter is right hand thumb rule. So in last videos we have discussed about the process by which we can find out that what is the direction of magnetic field, or in which direction a magnetic needle will deflect when current flows through a certain conductor. Okay, so here we will discuss that if suppose you know the direction of current, can we find out the direction of magnetic field lines? So the one rule is there, that is right hand thumb rule. The rule is like this, okay. Suppose if you keep your right hand in this way, pointing the thumb towards the direction of current. Suppose uh, here you have a conducting wire, and the wire is conducting current in this direction. Now if you keep your hand in this way, in such a way that the thumb is towards the direction of current, means like this, then magnetic field will be given by the curl of the other four fingers. So curl of the other four fingers is like this side. This is the direction of curl of the four fingers around the conductor, okay, in a circular way around the conductor. So this is the direction of magnetic field when current flows like this. Okay, again, suppose this is a conducting wire, current is flowing in downward direction. So if you are asked to find out the direction of magnetic field, you will keep the right hand in such a way that the thumb should represent the direction of current. So the thumb this time should be in downward direction, and if you keep the thumb in downward direction, you will see that the direction of current is like this, magnetic field is like this side, because your curl of your finger will be this side. Now you can try that your thumb should be downward and the curl of the other four fingers should be like this is the direction around the conductor. Okay, this is a straight conductor, around the conductor this will be the direction. So that's what is mentioned in this rule. You can see once what is mentioned here. It is given that if a conductor, this one, carrying current is imagined to be held in the right hand such that the thumb points the direction of current, then the tips of the curled fingers encircling the conductor will give the direction of magnetic field. Okay, so I hope it is clear. Now we will see what is a magnetic field. Okay, before we proceed for that, let us see two notation. This two notation, that means suppose if this kind of magnetic field is given, cross magnetic field, so any in some sums or maybe in any derivation, this kind of magnetic field. So what you have to remember, that if it is a cross magnetic field, that means the direction of magnetic field is into the plane of the paper, means it is going inside the plane of the paper. And if the magnetic field is given by some dot like this, some dots, that means this one, okay, some dots, that means this is the magnetic field which is outward. Outward means towards you. If you are suppose drawing in a paper, then it is not towards the paper but it is coming out from the paper, and if it is cross, it is going inside the paper. Okay, so remember these two notation, then we will proceed to next one, this part. See here, what is the value of magnetic force, and first of all, what is magnetic field? So the definition of magnetic field is given here, this one, just a second. Okay, the space or region around the current carrying conductor or a magnet within which its influence can be felt by the magnetic needle or any magnetic needle, or maybe it may be any other magnet also. Okay, I am telling you the definition in simple word. The thing is that, suppose if you keep a magnet here, so around this magnet a region will be created, within which, or within this region, if you bring any other magnet or any other magnetic substance means like iron, which is attracted by magnet, right? Iron or maybe other magnet. So what happened is, those incoming things means this magnet or maybe a piece of iron, they will feel the magnetic field produced by this, or they will feel some magnetic effect inside this region. If they go out from this region, they will not feel anything. So for what reason they are feeling this one? The reason is, this magnet is creating a magnetic field around it. So in simple word, what is magnetic field? It is the region around a magnet, or maybe by a current carrying conductor. Here, instead of magnet, if you keep a current carrying conductor also, then also around the conductor there will be formation of a magnetic field, within which if you bring any other magnetic material or other needle, or magnetic needle or magnetic material or magnet, then there will be either attraction or repulsion. Okay, so this region is called magnetic field, and the magnetic field strength is given by B, just like electric field. I think you remember electric field concept. There was also the concept was same only, that there was a charge, and around the charge there was a region, within which if you bring some other charge, then the effect of the first charge can be felt. So magnetic field is also same way. Okay, like electric field is given by E vector, magnetic field is given by B vector. B means strength of magnetic field. Okay. Now, like electric field, when there is a electric field, if a charge enters in the electric field or a charge is kept in the electric field, it experiences a force which is F is equal to QE. I think you remember this one. So in the same way, if a magnet or if any magnetic material is kept in a magnetic field, then also it should feel some force, some magnetic force. What is the expression for that magnetic force? So remember that the expression for magnetic force is this one, okay. So here one thing you can see, that F is equal to Q into, Q means the charge which is there inside the magnetic field. So this charge into V cross B. Cross means it is the cross product of what? Of velocity of the charge and the magnetic field within which the charge is kept. So from this formula, can we say one thing? Can we infer that if that particular charge is not having any velocity, or if the charge is at rest, that means no magnetic force will be felt by it. But in electric field it was not like this. In electric field, in fact, if the charge is static or at rest, it will feel the electric field force, because F equals to QE only. V was not there. But in magnetic field, remember that the charge has to be in motion. It must have some velocity, then only it will feel the magnetic field. Okay, now we will focus here. Cross product. I think you remember the concept of cross product from class 11. What was that? If you remember, the concept was like this. Suppose we have two vectors, vector A cross vector B. Their resultant is vector C, like this. The meaning is that the direction of vector C, this C will obviously be a vector. Whenever two vector undergo cross product, their result is always a vector. That is why cross product is also called vector product. Anyways, the direction of this C will be perpendicular to the plane containing A and B, and we can find out the direction of C again by right hand rule. Okay, how we do so? The thing was like this. Suppose if we have two vector A and vector B, suppose vector A, vector B. Now if I ask you, find the direction of vector C, which is nothing but A cross B. So what you have to do, you have to imagine, since C is equal to A cross B but not B cross A, so you have to imagine that A is moving towards B. Which direction? This direction. I told you about this one in class 11. So since A is moving towards B, in which direction, if you just keep your right hand in this way, the curl of this forefinger and this direction is matching, right? Same only. So where is the direction of your thumb? Upward. So the direction of vector C will also be upward towards the thumb. Okay. If I write, okay, if I write C is equal to B cross A but not A cross B, if I say it is B cross A, then what will happen? Then we will consider B is moving towards A, and in that case you have to keep your or hold your right hand in this way, in such a way that the thumb should face in downward direction. Your thumb will be like this, then only the curl of your forefinger will be in this direction. So that means we know that thumb is representing the direction of vector C. So in this case vector C will be downward. But in any way, whether it is upward this side or downward, it is always perpendicular to the plane where A and B is lying. If A and B is lying in xy plane, then the direction of C will be either in positive z axis or in negative z axis. Okay, but always perpendicular to the plane. So here here also same thing will happen in this formula, because see here the thing is like this. F, you can write suffix m to show that it's a magnetic force, or simply F also you can write, not a problem. Then Q, V cross B. See, this is resembling this concept, the concept that I said just now, C equal to A cross B, because here this charge is a scalar one, so it has no role in determining the direction of F. So see, F and C same, V and A same, B and B same, Q it has no direction, no such role. Okay, so it is a scalar. So in this way we can say that the direction of force will be always perpendicular to the plane containing V and B. By this formula we can say. Okay, fine. And how we can get the direction of force? By this rule. If we know where V is lying, if we know where B is lying, then we can find out F. See here, V cross B, right? So V is moving towards B, we have to consider in this way, and that is why the curl of four fingers are like this, and thus the thumb points in which direction? Upward. So that means the force is also in upward direction. Okay, I think this much is clear. Then one more topic we'll discuss in this video, a small one. This part, dimensional formula of B. Okay, they have calculated the dimensional formula in this way, but you can remember also, you can remember the dimensional formula, you can learn this one. That dimensional formula is this one directly. If you want, you can go see the process also, but otherwise you can remember this one. B, the dimensional formula is m L0 T minus 1 A minus 1. A stands for ampere, and the unit of B is Tesla. We call it Tesla. This is the SI unit of magnetic field intensity. Okay, this Tesla can also be, it can be broken in this form: 1 that like 1 Tesla equal to 1 Newton per meter per ampere. That means Tesla is nothing but Newton per meter per ampere. Okay. And another thing, this is the SI unit is Tesla, which is in short we write it by capital T, but the CGS unit is Gauss, okay, capital G. The relation is this one Gauss equals to 10 to the power minus 4 Tesla, or 1 Tesla equal to 10 to the power 4 Gauss. Okay, so for this video this much. In next video we'll discuss about Lorentz force.